Gauss's law is a rule that was derived, believe it or not, by someone named Gauss, and it is closely related to flux. So in order to investigate Gauss's law, we're going to look at what happens if we have a point charge, and we're going to consider the flux through a sphere. Oh, I went too far down there. Oh well. We're going to consider the flux through a sphere, an imaginary sphere around the charge. Just as a point of reference, this is called a Gaussian surface, just because there's nothing actually there. We're just considering the flux through this, spherical shell that is, not actually a physical object. Okay. We know flux is E field cosine theta times area. All right. Well, we know that the E field of a point charge is kq over r squared. Now, if we consider this surface, the E field points directly away from this positive charge, and since this is a sphere, all of the field lines are going to be perpendicular to the surface. And if they're perpendicular to the surface, the angle between the field and the normal to the surface is 0. So that's cosine of 0, which of course is 1, times the area. And the surface area of the sphere is 4 pi r squared. So we can see here, it doesn't actually matter how big the sphere is. The values of r cancel out, and we're left with a flux equal to 4 pi k q. Now k, I think I mentioned this before, that k is actually a contrived constant. It doesn't correspond to something physical. K is actually equal to 1 over 4 pi epsilon naught. And epsilon naught is actually, a physical constant. It is 8.85 times 10 to the minus 12th. And that is coulombs squared per Newton meters squared. And epsilon naught is called the permittivity of a vacuum, or sometimes the permittivity of free space. It is a physical constant that has to do with how well or how much electric fields are able to transport through something. There's epsilon naught, which is the vacuum permittivity, and then there are different materials have different values of epsilon. But that's not what it is. Isn't super important right now. But what is noteworthy is that if we plug this in for k, 4 pi, and then k is 1 over 4 pi epsilon naught, our 4 pi's go away, and we just get that the flux is equal to q over epsilon naught. Now, this is the result for a point charge, but it turns out that for any charge and any surface, that the flux through that surface is equal to whatever charge is inside it, Q, E, and C. E and C stands for enclosed, so this is the enclosed charge. Whatever charge is inside the surface over epsilon naught. And this is Gauss's law. That whatever charge is enclosed in the surface, only the charge enclosed in the surface determines the flux through that surface. Yep. And we kind of went backwards because I told you the Coulomb force and the electric field of a point charge and whatnot. But Gauss's law, finding this Q enclosed over epsilon naught and then equating it to this E cosine theta times A, which is actually a cross product that's integrated, or dot product? A dot product that's integrated, for those of you who know what a dot product is. So if you equate this Q enclosed over epsilon naught to this value, that's generally how the E field before any sort of charge distribution is derived. So for, we have a surface near this Gaussian surface near the point charge. Using Gauss's law, Q enclosed over epsilon naught, if we set that equal to E cos theta times area, that's what will wind up deriving the electric field of a point charge, getting us that kq over r squared. And we can use Gauss's law to find the electric field of charge distributions that we don't really know stuff about. So for example, let's say we have a charged insulating sphere with uniformly distributed charge. Right. Now, if this was a conducting sphere, all the charge would be on the surface. But since it's an insulating sphere, the charge is uniformly spread out throughout its whole volume. Okay. Let's say this sphere has total charge big Q. It is worthwhile to define a no, we don't need to do that. It has charge big Q. Now, outside the sphere, if we consider a Gaussian sphere outside this sphere, the flux through it is just going to be big Q over epsilon naught, and its electric field will be the same as a point charge. Let's consider the electric field inside the sphere at some point. All right. And a big part of applying Gauss's law is choosing the appropriate surface. If an electric field is radially symmetric, like this one, it's a good idea to use a Gaussian sphere. If it's a point charge, if we have a wire, that has some kind of charge, then the electric field is radially symmetric, but really it's radially symmetric in a different way. And for this, it's a good idea to use a Gaussian cylinder. Okay, so depending on because we want to pick a field where it's a lot easier to do calculations if we pick a field where the electric field is perpendicular to the surface. So for an insulating sphere, we want to pick a sphere. But to figure out the electric field inside the sphere, we need to pick a sphere that's centered on the center of the circle, but it has a smaller radius than the radius of this charged insulating sphere. Right? We'll say this charged insulating sphere has a radius of capital R. So our flux through our Gaussian surface is equal to Q enclosed over epsilon naught, right? Well, this Q enclosed is some fraction of the big Q, okay? And the fraction of the big Q is the total of the big Q would be in a volume of 4/3 pi big R cubed, right? The fraction that's inside is 4/3 pi times the radius of our Gaussian sphere, which we'll call little r cubed, over epsilon naught. And we know this is equal to our electric field times cosine theta times our area. Well, this electric field is going to be radially symmetric, which means that our cosine theta is cosine 0, which is 1. And this area is the surface area of our Gaussian sphere. So on the left side, we've got Q, 4/3, and the pi's cancel out. We've got an little r cubed over big R cubed. We've got an epsilon naught on the bottom. And then that's equal to our electric field times the area of our Gaussian sphere. And so then a factor of r squared cancels out. We move the 4 pi over, and we get the electric field at a point inside the surface is equal to Q times little r over 4 pi epsilon naught times big R cubed. So that is the electric field at any point inside an insulating sphere with uniformly distributed charge. Electric field actually increases as you get further from the center, primarily because there's more, the amount of charge enclosed is growing at a rate proportional to r cubed, while the surface area is only growing at a rate of proportional to r squared. So you can see how Gauss's law is kind of handy for figuring stuff out. I think on the homework you will use Gauss's law to derive the electric field of a charged wire. We're also going to apply Gauss's law to figure out a capacitor's electric field. To define the electric field of a capacitor, we're going to use Gauss's law. Let's remember a capacitor is two parallel plates, and the top plate has a charge of positive Q, or well, it doesn't matter, top or bottom. One is a charge of positive Q, one is a charge of negative Q. Okay? And there's an electric field that goes essentially straight down, perpendicular to the sides. Now, in order to do this, it's useful to define a charge per unit area. Our capacitor it's two plates, so it's like that's too big. So it's like we have these two things. Generally, they're the same size, but they have some area that the plate of the capacitor takes up, and it's useful to define a charge per unit area, and we call that sigma. Which is the same variable as the Stefan-Boltzmann constant from thermo, so deal with that. And it's just a charge per area. It's Q over A, the area of the plate, and it's going to be useful to define that as we get into doing this calculation. Right. For the electric field of a capacitor, we want something that will hit this surface perpendicularly. So we can go ahead and use what is useful to use is a Gaussian rectangular prism, I guess. So that is partially inside the capacitor and partially not. So it's going to look like that from a side view, but remember this is 3D, so that this has some sort of surface area if we rotate that. Our flux through that surface, as we know, is Q enclosed over epsilon naught. And the Q enclosed is going to be equal to this this sigma times the area of our surface. And the area of our surface, I'll just call that, well, it's the length times width of our Gaussian rectangle. So that's the charge that's enclosed. That's over epsilon naught, and we set that equal to our E field times cosine theta times our area. And well, this area is also length times width. So actually, those areas cancel out because the enclosed charge is proportional to area. But the flux is also proportional to area, so those proportionalities cancel out. And again, our field is perpendicular to the surface, so the bottom face of the rectangle, this theta is 0, and so we get cosine 1. For the side faces, the electric field is parallel to those surfaces, and so this is cosine 90. So those surfaces don't contribute to the flux because you get a 0 over here. So this is 1 for that bottom surface, and our electric field is just sigma over epsilon naught. And that's really why it was useful to define sigma, because this field comes out to be just that sigma over epsilon naught. So you can see it by skillfully picking our surface, we can figure out electric fields of different charge distributions by using Gauss's law.